To understand game theory, we must analyze the results of each player's actions. Here, player 1 and player 2 each face decisions with different outcomes. For example, if both confess, they receive a penalty of 3 years each. If player 1 confesses and player 2 denies, player 1 walks free while player 2 receives a 5-year sentence. The same applies in reverse. Lastly, if both deny, they each face a minor 1-year penalty. Here is an outcome table summarizing the results. It provides a clear view of the potential penalties for each combination of actions. Notice how the dominant strategy can sometimes reveal itself as we consider which actions yield the highest payoffs for both players. In this case, confessing is the dominant strategy. It consistently results in a better outcome for each player no matter the other player's choice. Denying is a strictly dominated strategy, meaning it always leads to worse results. Game theory teaches us to avoid dominated strategies in decision making. But why might someone ignore the dominant strategy? Factors like trust, risk tolerance, and communication constraints play a significant role. For example, in the prisoner's dilemma, collusion is risky because each player has an incentive to betray the other for personal gain. This introduces the possibility of exploitation. Iterative elimination of dominated strategies simplifies more complex games. Take this table, for example. Both players must think strategically, eliminating strictly dominated strategies one by one to converge on an optimal outcome. This iterative process assumes rationality and intelligence from both participants. After applying the iterative elimination process, we determine the optimal solution. Both players should choose either option 2 and option B. This results in a payoff of 3 for each. This method highlights the power of game theory in identifying mutually beneficial strategies. Now, let's explore zero-sum games, where one player's gain is another's loss. A classic example is rock, paper, scissors. The net sum of payoffs is 0 for any pair of moves, illustrating the competitive nature of these scenarios. Next, we look at Nash equilibria. A Nash equilibrium occurs when no player can improve their payoff by unilaterally changing their strategy. Imagine two drivers at a junction. If one goes and the other stops, both avoid a crash. This is an example of a Nash equilibrium, as neither driver has an incentive to change their action. Breaking down complex social interactions into smaller, trust-building steps can help align incentives. For example, when managing a team, ensure that cooperation yields better outcomes than working independently. This builds trust and fosters collaboration. When facing sophisticated opponents, adopting a minimax strategy minimizes the worst possible loss. This approach is useful in high-stakes negotiations or competitive markets, ensuring the least damaging outcome even in adverse scenarios. Finally, patience is a critical asset in strategic decision-making. Hastily adopting a race-to-the-bottom strategy can lead to mutually detrimental outcomes. Instead, focus on long-term benefits and sustainable practices.